Exponential functions have the characteristic that they involve a base raised to an exponent, and the exponent is the variable, or is it expression involving the variable. This is distinguished from a power function where your variable is the base. Notice x is up here in the exponent for an exponential function. It's down here for the power function. It's the variable raised to some power. Big difference. A polynomial function is a sum of multiples of power functions where all the powers are integers and not negative. So we have a fourth power, a third power, a second power, and a zeroth power, because 7 means same as 7 times x raised to the 0, because x raised to the 0 is 1, and 7 times 1 is just 7. So this is a sum of multiples of power functions. The power function x to the fourth multiplied by 7, added to the power function x to the third multiplied by 5. Then we subtract the power function x squared times 3, and then we add the power function 7x to the 0, or just 7. The degree of the function is the highest power. In this case, the degree is 4. A quadratic function is nothing but a polynomial of degree 2. Okay, so here's a polynomial of degree 2. All positive powers, c times x to the 0, b times x to the 1, a times x squared. Highest power is 2, so the degree is 2. This is a quadratic function. And a linear function is a polynomial of degree 1. Okay? It's just mx plus b, one of the standard forms of a linear function. There are other standard forms, but it's just m times x to the 1 plus b. And any other form of a linear function can be put into this form. You just solve for y. Okay. Now, a few things about these functions. One of the big deals for exponential functions is that y equals b to the x is equivalent to log base b of y equals x. So if we want to solve this equation for x, we just convert it to logarithmic form, and we calculate log to the base b of y using the rules of logarithms. If we want to solve y equals x to the p, well, first of all, let's just turn it around. X to the p equals y, because x is what we're trying to find. We'll put it on the left. So that if we raise both sides to the 1 over p power, x to the p raised to the 1 over p is just x. And that's then equal to y to the 1 over p. Now, why is x to the p to the 1 over p just equal to x? Well, a to the b raised to the c is a to the b times c. So x to the p to the 1 over p equals x raised to the p times 1 over p, which is x to the 1, which is just x. So x to the p to the 1 over p is just x. And we have a slick way of solving the power function. Now, of course, these relationships can be disguised, and I'll do a couple more examples within a bigger equation. But if you follow usual equation solving procedures, you will often get to something like this or something like this. Or in a logarithmic equation, you might get this, which can be converted to this if you wanted to find y. Okay, talk about polynomial functions in a minute. Quadratic functions. Main thing that you want to know about quadratic functions is that ax squared plus bx plus c equals 0 if and only if x is equal to, well, this is the quadratic formula, okay? I won't read it to you. You should know it backwards and forwards by now. And this gives you the zeros of ax squared plus bx plus c. In other words, the points at which this expression has value 0, the points at which y equals ax squared plus, the graph of y equals ax squared plus bx plus c would cross the x-axis. And linear function, easy to solve this for x as long as m is not 0. Now, polynomial functions. The main thing we need to know about polynomial functions is that any polynomial function turns out to be a product of linear and irreducible quadratic factors. Now, an irreducible quadratic factor is a quadratic factor of this form where b squared minus 4ac is less than 0. Okay? So we can say down here, first of all, no real zeros if b squared minus 4ac is negative. Okay? So by an irreducible quadratic, if this is the case, the quadratic is irreducible. So a product of linear and irreducible quadratic factors could look something like this. You have m1x plus b1, where m1 and b1 are just numbers. m2x plus b2, where m2 and b2 are just numbers, probably not the same as m1 and m2. And then a1x squared plus b1x plus c1, where a1, b1, and c1 are numbers. And a2x squared plus b2x plus c2, again, no reason to think that the numbers a2, b2, and c2 have anything to do with a1, b1, and c1. Okay? Now, quadratic factors would be irreducible. If not, if they have zeros, they can be factored. So they could be written like a product of two linear factors. So this is the way a polynomial would look if it was reduced down to its fundamental factors, okay? Any polynomial can be factored to look something like this. Now, you might have more than two linear factors or fewer than two. You might have more than two irreducible quadratic factors or fewer. Now, I've written under here, this is irreducible, meaning b1 squared minus 4a1c1 is negative. This is irreducible, meaning b2 squared minus 4a2c2 is less than 0. If they aren't less than 0, they are factorable. That doesn't mean you can necessarily easily find exact factors. Maybe you can't find exact, well, you can find the exact factors for any reducible quadratic just using the quadratic formula. Okay, and over here I've written down that this factor is 0 for x equals negative b1 over m1. This factor is 0 for x equals negative b2 over m2. So this particular quadratic would have a 0 corresponding to this factor, a 0 corresponding to this factor. Since these are irreducible, there are no zeros. So we only have the two factors, so the polynomial might look, the graph of the polynomial might look something like this. It goes through 0 at negative b1 over m1, which is a solution to m1x plus b1 equals 0, and negative b2 over m2, which is a solution to m2x plus b2 equals 0. So you have these 2 points where the graph goes through the axis, the x-axis, and if m1 times m2 times a1 times a2 is negative, the graph will go down this particular graph would go down into negative numbers. That would be the end behavior. Now I'm not going to get into a complete discussion of that, just reminding you of all that kind of reasoning that we've been over earlier.